briefly explain. I would like to work out one gate problem also, and explanation to this also will be explained. And subsequently, I will explain various other theorems like Millman's theorem, and one problem on that, substitution theorem, and intelligence theorem. And then, if time permits, then I will go for the other theorems also, compensation theorem, and subsequently, I would like to answer the queries that have been raised for yesterday's this one. So, of course, they are less in number, so last 10-15 minutes may be enough. And so, I hope you are able to follow these things. And now it is right at 3 o'clock. So, I would like to start the session. And reciprocity theorem. So, I would like to briefly explain this because yesterday I have spent on this particular one about half an hour. Yeah, in any electric network consisting of linear bilateral passive elements, which is represented as a two-port network, the ratio of excitation at port 1 to the response at port 2 will be unaltered if the excitation is at port 2 and the response is at port 1. That is, the positions of the excitation response are interchanged and the network is unaltered. That is a statement. And this is the explanation that is being given. Ratio of V1 by I2 dash. This current is I2 dash. And you have to follow this in notation, which is to be consistent if you want to have the commonality of this one. Okay. So current, even this is applicable to the other two-port network parameters topic, which I am going to discuss after the theorem, maybe tomorrow or day after. So next topic will be two-port networks after the theorems are being completed. Theorems include the Maxwell's circuiting current theorem and the nodal analysis combined theorem also. After that, I will be discussing the two-port networks. Anyway, with respect to parameters. So I1 and I2 are the port currents into the port is taken as positive. Follow the same convention. Current into the port is taken as positive sign convention. And similarly, V1 and V2 are the port voltages. That is, one is at higher potential compared to 1 dash. That convention will follow. Or there is a rise from minus to plus from 1 dash to 1. Similarly, from 2 dash to 2. The same convention will follow. So we mean to say ratio of V1 by I2 dash. So this should be I2 dash. That is, and similarly, when you interchange the positions of the voltage here, this is I1 dash. So excitation and response are interchanged. The ratios will be same if the same voltage is being applied. So then the current also will be same. If V1 equal to V2, I1 dash will be equal to I2 dash. Now I have given 6 specific points here, which I have explained in detail here. So I just briefly repeat it. If excitation is voltage source, response at port 1, port 2 is to be short circuit current. And vice versa. Why and all I have given an explanation through a simple example also. If the excitation is current source at port 1, response is to 2 and vice versa. Now, if the excitation is voltage source at other port, there is okay similar. So here voltage source and open circuit voltage. Short excitation is current source and short circuit current. Both are of the same type or not permissible in this because ratio will not be obtained. That is a property of the network for a reciprocal network or for a passive network. And if the first two conditions are satisfied only, it is stated as the reciprocal network. And in general, passive network would satisfy the reciprocal theorem are called reciprocal networks. Okay. Even if these two are not satisfied, still the first two conditions, if they are satisfied, they are called reciprocal networks. This only indicates that the point number 3 and 4 indicate that we should not take if the voltage source is on one side, you should not take the open circuit voltage for the measurement to verify the reciprocity theorem. Not that it is wrong. Okay. The statement of the theorem says it should be opposite. Yeah. Next. And similarly, if it is a current source that is being chosen, then short circuit current at port 2 and vice versa. Current source and port 2 is short circuit current, you should not take. Similarly, at port 2, if you have got a current source, you should not take at port 1 the short circuit current. Right. So that is the meaning of these statements. So 3 and 4 only to show that it is not possible. I have taken some example also. So passive network which satisfies the reciprocal theorem are called reciprocal networks. Okay. So that is why I have given this particular statement. If reciprocity theorem is applicable, then every passive network will be a reciprocal network. Right. So consider the network. Just to show the example. This example, somebody even stated previously. Even asking the question is, I have given an example like how that question can be asked for the object type. It's not that. Some are explanations, some are gate questions and other things. Okay. Consider the network 1 ohm, 2 ohm, 2 ohms. Find the ratio of excitation at port 1 and response at port 2. And not only that, in the object type questions, in blanks or otherwise, questions can be asked. It's not that only the multiple choice questions are being asked. So therefore, questions can be there in this particular one. Excitation voltage source at port 2 and the response, that is open circuit voltage at port 1. This is how I explained. I will briefly mention it. The circuit is shown here and the circuit is being drawn here because I have given sufficient explanation to this. Only thing I want to explain this is we have done using the symbol called element currents or branch currents, etc. Okay, so these two are in parallel. When this is shorted, when the voltage source is taken as assumed, this 4 volt source excitation. So this is 2 into 2 is by 2 and 2 are in parallel gives you 1 ohm. This is in series, so 1 plus 1 is 2 ohms. So total current is equal to 2 amperes and current through 2 dash will be generally 1 ampere. So therefore, now here the point is sign convention is very, very important in this case. Port current is into the port is taken as positive, so it is generally these current short circuit currents are away from the port. Right? So therefore from 2 to 2 dash. That is why I would like to call that as I2 dash will be equal to minus I2. I2 dash or I2 dash equal to minus I2. Because current is away from the port. So we have got the response is excited and the response in magnitude is 4. A similar question that is being asked in the gate, I will tell you why you have to be so particular about the sign convention, although magnitude is correct. So they are very particular about the sign conventions also. And that sign convention is being justified not only in this particular one. There is another statement that is mentioned with respect to electronic circuits also. And even the Maxwell's loop current method also is equally applicable in that for verifying that particular one. I will tell you that statement subsequently was negative current. It is the direction of the sign convention that is being chosen to be negative because it is away from the port. So now the second case is the voltage source is put in port 2 side and we have to measure this short circuit current which is to be I1 dash. I would like to call this as I1 dash should be same as minus I1. That is what I have mentioned, right? So total equivalent resistance is 2 and 1 are in parallel from this side because you should not remove the source here and then try to do it. Now you have to do the equivalent resistance to find the total current delivered by the 4 volt source. You have to start from other end. That is simple logic. So 2 into 1 by 2 1 is 2 by 3 is the equivalent resistance up to this point. Plus 2 is the 2 by 3 plus 2 is 8 by 3 is the total equivalent resistance or equivalent. Therefore total current is 4 divided by 8 by 3 is 1.5 amps. And current through port 1 dash is 1.5 into 2 by 2 plus 3 gives you 1 ampere from 1 to 1 dash. 1 to 1 dash direction of the current is away from the port, though therefore it is minus I1 which is same as I1 dash in the rotation that can be followed. Although I have not explicitly put here, I have not put it here but that is implied. So therefore ratios are equal. So therefore the network is reciprocal. Now to say that you should not take when the excitation is the voltage source, you should not take the open circuit voltage measurement for the ratios to be obtained. I have given these two are the examples for finding. So now to find the open circuit voltage at port 2 when V1 is excited with the same voltage source 4 volts. So now you can see when this is open, this 2 ohms resistance is ineffective in that sense because it is open. So this is only a voltmeter, not the source. Remember that. It is open circuit voltage means if you put V inside, that is implied that it's voltmeter, which we follow the convention. outside this one, if you don't write and you write like that, 1 plus 2 is 3, right? No current flows through the 2 ohms, therefore there is open here. And 3 ohms resistance in series, 1 and 2 are in series. So V1 by 1 plus 2 is the current multiplied by this 2 voltage will be appearing across it. No current is flowing through this band. So therefore there will be no potential drop. These two are connected. So this resistance is connected across the port 2. So that ratio of the voltages can be at a later stage as the voltage gain, or similarly when port 2 is excited with voltage source, you want to tell you want to get the V1, which is the voltmeter, that is open circuit voltage at port 1 dash. So now you can see this is open as far as this circuit is concerned, because no current can flow through this particular one, port 1 dash, because you are measuring the open circuit voltage. And so therefore 2 and 2 are in series from the V2 side, port 2 side. So therefore V2 is given as 4 volts. So therefore ratio of excitation to the response that is being chosen here, 4 by 2. So therefore it is 2. So you can see these ratios are not equal, right? So therefore the third and fourth cases should not be taken. That is the only thing. There are statements, proofs and other things might be there, which is out of context. What we want is only the concept to be understood. Now, let us see this particular problem. This is given in GATE examination, I think. Yeah, GATE 2000 for 2 marks. Okay. Use the data of figure A. The current I in the circuit of figure B. Okay, use the data of figure A. The current in I in circuit of figure B will be, that is implied, 2 amps given, 2 amps given, minus 4 amps and 4 amperes. Now you can see the values of the resistances. It is a typical circuit. 10 volt source is given, 2 amps of current is flowing through this particular other end, right? This can be treated as the port 1 side, this can be treated as the port 2 side, right? Port 1 is excited, it is 10 volts, port 2 is response is 2 amperes. So R1, R2, R3, R4 are the resistances. The values are not being given. Now look at figure. What happened in figure B? The voltage source is being taken as 20 volts. So 10 volts multiplied by 2. And current is flowing through this. 2 amps, minus 4 and 4 amperes, and it is a gate question for 2 marks. Now the ratio of the excitation to the response is, so here this is V1 is equal to 10 volts and I2, that is minus I2. Minus I2 means it is I2 dash. It is not the negative current, as I mentioned, it is only the direction. So 10 by 2 is 5 amperes. Right? Ideally speaking, V2 by V1 by minus I2 must be same as V2 by minus I1. Or V1 by I2 dash must be same as V2 by I1 dash. So this must be 20 by I1, minus I1. Now how to get this? Current is here, the current is delivered by the source V1. So their ratio 2 must be same as ratio 1 according to reciprocity theorem. But in the sense, here the ratio is only 2, but the voltage is being given. The ratio is, because if it is 10 volts only, that will be same current, 2 amps. But the voltage that is being given as 20. So the ratio, even though it is same, it gets now doubled because of that voltage difference. And now see the sign. It is in the opposite direction because it is away from the port. 7, right? The current flowing through this is 4 amperes is right, but the answer that is being given 4 or minus 4, which is to be chosen, right? So both are seem to be correct as per the convention, right? If you ignore the corresponding sign convention, the ratio is same. But if you follow together with the ratio and also the sign convention, then it is minus 4. Okay, so minus 4 is the correct answer. So always this will be misleading. We never generally bother about this particular one, but explicitly if you want to say, it is minus 4 amperes is the right answer. Now I will go to explanation to this. Earlier also I have stated the ratio of response to the excitation on the opposite side. So therefore the sign convention is never bothered earlier. Most of the times ignored. Not that it is that is a mistake from our side. Okay. Now we see what is the statement engineering the subject textbook. But this is being done, and So consider two loops A and B of a network N. This is the definition of the reciprocity theorem in another way. And if an ideal voltage source E in loop A produces a current in loop B, then the interchanging the positions of an identical source in loop B produces the same current in loop A with opposite direction. But absolutely, this is also loop current. The voltage source is 10 volts here. This is nothing but the loop current itself. This is another loop, right? So excitation voltage producing the current in this direction, right, which is away from the port. So making excitation on the other side, this loop current will be also in the opposite direction because port 1 to 1 dash is the current in port 1 will be into the port is taken as positive. This will make the circuit that is without a closure path, no current can pass through. It becomes open. So therefore, in this context, although we talk in terms of so far is branch current that is only considered, the branch current is due to the loop only, loop current. Loop current means it is a current flowing through this particular circuit of R3, R4 and this one, consisting of the terminals 2 to dash perhaps, right? So that convention is to be followed carefully. Right? Difficult one to understand, and this is a theorem which is being applicable in antenna propagation also, as I have said. I do not know about antennas I mentioned. So even now, still we have not studied anything in that, but in one of the textbooks they have given that reciprocity theorem is applicable for antenna circuits, right? So you consider the source excitation here and find the loop current here, and when they are interchanged, it is equivalent to this is giving one direction and this is in the opposite direction to the port. So there, similarly, this excitation is also giving the port direction is not into the port naturally, it is away from that. Now I can make you confusing that if I reverse this, yes, if I change the voltage source here, then the direction of this one will be into the port. So similarly, when do this, that also will be there. You do the same excitation which is reversed one, and then I will be into it. So that is not being stated, but that is the explanation. In one of the textbooks that is also being given. Consider the two loops A and B of a network N, and if an ideal voltage source E in loop A, because that means they are saying that this is loop A, this is in loop B, naturally. There are other loops in the circuit also, but between two loops, it is in one loop, the source must be in one loop. The excitation is in one loop, the response is in another loop. So between the two loops, if the excitation, small spelling mistake, so homogeneity holds, and so when voltage source is doubled, the current also doubles. Okay, so with opposite direction. In the circuit, due to the excitation port 1, the loop current is in clockwise and away from port 2. Due to excitation at port 2, the loop current is anti-clockwise and is away from port 1. That is the meaning of this particular one. So that was the reciprocity theorem. I hope you have followed, and it may seem to be confusing, but if you are clear with the sign convention and the way in which it is being explained, I think clarity is there. Okay, so now we'll go to the next statement. So this is a very important theorem, Millman's theorem, MILL-MA-S-S. It is a noun form because it's the name of the although it is a noun. Okay, MILLI. So it is some scientist, I don't know where from he is originated, but I don't have the data of that. Anyway, now I will explain the Millman's theorem. So it is a very important theorem in one context. I will tell you the theorem and where it is being applied and all those things. So in any two-terminal network consisting of linear, passive, bilateral and multiple current or voltage sources are acting simultaneously across a pair of terminals, the circuit prior to the load can be replaced by a single equivalent source and in series with the equivalent impedance. This is same as open circuit voltage. Now, this is one type of the statement. The other one is direct computation of Millman's voltage also can be obtained, which I have not given, but I have given mathematically in this particular context. Okay, so yeah, so this is one type of statement. So it is that means there is a definite relationship between open circuit voltage of the Thevenin's and the Millman's theorem. That's what I would like to emphasize. In some of the textbooks, the difference between open circuit voltage and the Thevenin's voltage and Millman's voltage is not being specified. I would like to answer to this particular question and then try to explain with a simple example which I understood. So it's here I did not find any gate questions which are being solved. Due to lack of time, I could not do much exercise in this. But the theorem statements are very tricky, and you should be in a position to follow. Millman's theorem, substitution theorem, all these things are quite involved. So, in any two-terminal network consisting of linear, passive, bilateral, and multiple current or voltage sources are acting simultaneously across a pair of terminals, the circuit prior to load cycle load can be replaced by a single equivalent voltage source and series with equivalent impedance. That is, it is equivalent to Thevenin's voltage only. But you see, what are the conditions that are there? V1 is the voltage source, Z1 is its series impedance. I mean, it can be AC or DC, but in general, I have mentioned V1, Z1, V2, Z2, Vn, Zn. Oh, that is missing. So anyway, V2, Z2, Vn, Zn applied to ZL. So this can be, so open circuit voltage can be obtained by replacing each one of them by the current source. V1, Z1 as I1 in shunt with Z1 or in shunt with current source. That is derivation aspect of it. I do not generally do the derivations, but this that means the practical voltage sources are being converted. So it is implied that all the statements are not explicitly given in these particular ones, and the practical voltage source is to be converted. We assume here only practical independent voltage sources for this particular one, and there is no element between the parallel branches also. So it is like we have got a simple example of this is three-phase circuits. In three-phase generation voltages, this type of situation will occur. This is the phase voltage of one phase voltage of second, phase voltage of 3, etc. And there's the equivalent impedances per phase. So they are connected in series. It can be synchronous impedance also. So therefore, three balanced or unbalanced voltages, V1 in series Z1, V2 in series Z2, and V3 in series Z3. Generally, we assume in power system application generation is balanced. But nevertheless, it need not be so. It need not be equal in this context. So simultaneous application of the parallel voltages connected across a pair of terminals together with the load condition, you can find the open circuit voltage replacing them as the current sources. So V1 by Z1 is V1 into Y1, that is admittance. So algebraic sum of the currents is V1 Y1 plus V2 Y2 plus so on plus Vn Yn. And Y Thevenin is 1 by Z1 plus 1 by Z2 plus so on plus 1 by Zn, and this is Z Thevenin. So that means replacing the voltage sources by the internal impedances 1 by Z1 Z open circuit voltage. That's what we did. I mean, everything has not been given here. So why? Because this is not the type of the situation which I was trying to solve for the open circuit voltage and then finding the Z Thevenin. This is the n+1 source. The load impedance also directly taken into consideration. So there will be n+1 current generators. They use the term current generators. So V1, V2, V1 Z1 is one source converted to current source as V1 by Z1. So that is V1 into Y1 is the current into A, and connected across the shunt element for the current source, with V1 by Z1 is the current source. That means how this is being obtained, we apply the principle of superposition. That is derivation aspect of it. How do we derive it? Treating this voltage source as acting alone, shorting all these things, short circuit the terminals, remove the load, find the short circuit current. V1 by Z1 is the current flowing through this particular one due to V1 acting alone. So that is I1. In parallel with that, Thevenin's equivalent impedance for this particular row only is Z1. So V1 in parallel with Z1, that becomes transformed to I1 in parallel with Z1. So similarly, I2 in parallel with Z2 are the shunt impedances which we are taking. So the total shunt, and that is how you have to imagine, if you recall that derivation, because it looks like a derivation, but it's the equivalent circuit of that. So then you will get the open circuit voltage like this. Now, the another way of putting it is, so VOC Z Thevenin is obtained, and then you will get the corresponding output voltage here. So the equivalent circuit can be obtained as the Millman IL into ZL, and Z Thevenin equal to 1 by Thevenin. So what I mean to say is, now how this Vm directly can be computed, you can see V1 into Z1 plus V2 into Z2 plus so on plus V1 by Zn into Vn plus 0 into that is, I am taking all the n+1 sources. I am also imagining that there is a current source due to the load also, which is not there. So that means the current generated is 0, it is in shunt. So imagine like that. So that means equivalent to open. And because we are considering in terms of the admittances and voltage sources, so V1 into 1 by Z1 is V1 Y1, V2 Y2, V1 plus Vn Yn plus VL into ZL. So imagine the current source to be obtained together with directly. Then will the total admittance of the circuit will be including ZL is the Z Thevenin plus Y Thevenin. That is Y Thevenin plus Y load. So Y Thevenin is 1 by Z1 plus 1 by Z2 plus 1 by Zn plus this one. So it is replaced with a single voltage source and the corresponding this one. You get directly the Millman's voltage. Direct computation of the Millman's voltage can be obtained like this. So this is the Millman's voltage directly can be obtained. I will explain this through a numerical example or better illustration that you will observe. Okay. So now what are the requirements for this? What are the conditions? No dependent or voltage or current sources should be present. This theorem is applicable in power systems also. That means if you recall the zero sequence voltage in the sequence components of the currents and voltages in a three-phase unbalanced circuit, even though generation is assumed to be balanced, due to the unbalance in the load conditions, there will be potential difference between if the generation side as well as the load side. If the two star connected ones are not earthed and they are not being connected, then there will be a star point and the neutral potential, the potential between the two star points. That two star points neutral potential can be directly computed using the Millman's voltage. And then, in other fact, the Millman's voltage will be same as the neutral potential. Right? This clarity is required to be understood. How and all proofs are there, the subject is there, and already people have realized that it's all very well established theories are there. So neutral voltage will be computed as Millman's voltage itself. So the PD between star ungrounded generator to the unbalanced star connected load can be directly computed using the Millman's theorem, also referred to as Millman's voltage. So Millman's voltage is same as the neutral potential between the two star points of the generator ungrounded and the star connected load ungrounded. So there will be definitely potential difference. So it is not a desirable feature. Ideally speaking, the neutral potential must be zero. There should not be any potential difference between the two. This is the cause of the panicky for the neutral potential to be obtained, because that will cause further unbalance in the system. So that is why neutral should be grounded properly. Those things you would have studied in power systems are those things in theory aspect you would have studied in several cases. Okay. So this is one of the fundamentals as applied to the circuit point of view also you should understand this. Right. So this is what I would like to emphasize, that the relationship between VOC, Z Thevenin, ZL and VM. This I got my idea in this about 1.5 decade ago, and so I tried to verify this particular one. So I want to give you the example of this. So now I will explain through an example. Then maybe if you want yeah. So from the Millman's theorem, I hope you have followed. So briefly I will mention, Millman's theorem is essentially parallel connected components, voltage sources are being there, practical voltage sources are being connected across the terminals A and B, and ZL is the load. So these are being replaced by current generators. We can find out the open circuit voltage and the Thevenin's equivalent impedance, removing the load. That is one aspect of it. Direct computation of Millman's voltage, treating this as N+1 generators. Direct computation of Millman voltage is also there, and finding the IL and other things. So and Z Thevenin means removing the load, you get this as Y1 plus Y2 plus Yn only, right? And so using this equivalent circuit, Vm will be equal to VOC minus IL into Z Thevenin, because there is only one loop here. So it is same as the load voltage. That load voltage is same as the Millman's voltage. So Millman's voltage divided by IL. Remember that earlier in the Thevenin's theorem we have taken one source or one independent source, but this is a specific case of the parallel connected ones, that is simultaneous. This is equivalent to some of the parallel generators are being connected across a bus bar. Okay, for improving the voltage is to be synchronized. Voltage of the two generators or more generators have to be synchronized, and the capacities can be enhanced to boost up the power supply sources. So at the grid side or otherwise, that is how we do the grid connections, right? So grid power supply is to be enhanced. The voltage of the generators must be connected to the bus bar, and the power capacity will be enhanced. So in that context, the simultaneously the generators are with respect to their impedances are considered to be connected in parallel across a bus bar. Okay, that is how you can imagine this particular one also. This is quite involved. This one, people, I don't know how much you can digest this one, but anyway. So now I would like to give a typical question here. It's not a problem for get answer, but it is explanation like. So I have devised the own problem for this, right? So please bear with me and see any difficulty is there. You can always ask the as queries, and that's what we are doing. So for the circuit shown in figure, find VM, Millman's voltage, IL, the load current, and the open circuit voltage, and verify the relationship between VM, V Thevenin, IL, Z Thevenin, ZL. So I will explain this in several parts. Okay, right? So for the circuit shown in this comma, find VM, IL, and VOC, and verify the relationship between VM, V Thevenin, IL, Z Thevenin, and ZL. So the voltage source that have been given are 5 volt source. They are independent practical voltage sources, 5 volts and 1 ohm resistance, 10 volts, 2 ohms resistance, and their load is shown to be 3 ohms. Okay. So that is by notation for this particular one. AB is the load pair terminal, and V1 is equal to 5 volts, V2 is equal to 10 volts, R1 is equal to 1 ohm, R2 is equal to 2 ohms, and ZL is equal to 3 ohms. So open circuit voltage is using Thevenin's theorem. Remove the load. Okay, that I have not shown here. Remove the load. That is implied now. So this is to explain the notation I have mentioned. So remove the load, find the open circuit voltage. So that will be obtained as V1 Y1 plus V2 I2 by Y1 plus Y2. How this can be obtained? The numerator is V1 Y1 is current generator. This one. V2 I2 it is this current generator divided by the impedance. So reciprocal impedance. So total current multiplied by the total impedance of the circuit of the Thevenins will be the open circuit voltage. So this is equivalent to V1 Y1 plus V2 I2 will be equivalent to the Norton's current or short circuit current only, although not explicitly being given. That is a part of the derivation aspect of the Thevenin's voltage to find for parallel voltage sources. And one more condition is that there should not be an element between these two, right? An element should not be present between the parallel branches. Directly they must be connected in parallel. So element means the resistance or other part of the elements should not be present in the between the parallel component. That is this particular place. So V1 Y1 plus V2 I2 by V2 Y2 V2 by Y1 plus Y2. So that is how you get this as 20 by 3 volts. So 5 into 1 by 1 plus 10 into 1 by 2 plus 1 by 1 by 1 by 1 plus 1 by 2. So this gives you 20 by 3 volts. Now let us see next one. Now Z Thevenin. Z Thevenin is equal to 1 by Y Thevenin. Y Thevenin is 1 by Y Thevenin is 1 by R1 plus 1 by R2. There are only 2 by 11, which is obtained. Multiplied by ZL. IL into ZL. So 3. So it's 60 by 11 volts. Now I want to verify this particular one. VM is equal to VOC minus IL into Z Thevenin. VOC is 20 by 3 minus IL is 20 by 11 into Z Thevenin is 2 by 3 is obtained as equal to 60 by 11. Same thing directly can also be obtained by using the formula. VM is equal to V1 Y1 plus V2 Y2. This is Y2. Looks like YL, sorry. So V1 Y1 plus V2 Y2 plus so on plus 0 into YL, 0 into VL divided by Y1 plus Y2 plus YL. Directly use the 60 by 11. How and not? This is the for the sake of explanation I have given maybe various ways of finding out this particular one. So if you want to come to directly Millman's voltage straight, you use this particular formula. How you form this formula has been obtained in some of the textbooks. It is not being given. You have to find out this, find out the equivalent circuit, VOC, Z Thevenin, and other things. In Millman's voltage, how Thevenin's voltage will come? So that is because of this reason. There is a definite relationship between these quantities, but direct computation of the Millman's voltage will give the calculations for the power system applications, which we know at least that it is directly representing the neutral potential, the potential difference between the two star points, and they are not grounded, and there is an unbalance in the system. Okay, so which is computation of the or it is also directly gives you sometimes the zero sequence voltage in certain cases. An unbalanced voltages can be resolved into symmetrical components, zero sequence, positive sequence, and negative phase sequence voltages. Millman's voltage is equal to zero sequence voltage that can be computed sometimes. So all these things are similar, but that is application aspect of it. I am only representing the statement of the theorem from electrical circuit point of view for this particular subject. But having got the exposure in these things, I thought I can share my views in this, not to get confused in this. Okay, and so this is the typical one. I would like to just briefly mention once again because there is so much of terms and theory that is involved in this. So for the circuit shown in figure, find Vm, IL, VOC and verify the relation between Vm, Vthevenin, IL, ZL. V1 is 5, V2 is 10, R1 is 1 ohm, R2 is 2 ohms, ZL is equal to or RL is equal to 3 ohms. So VOC is equal to remove the load, which is not shown here, remove the load. There are only two generators here. The open circuit voltage will be equal to Norton's current multiplied by Thevenin. Norton's current is V1Y1 plus V2I2 because it is 20 by 3. Now, Thevenin is obtained as 1 by Thevenin is equal to by 3. IL is equal to VOC by Thevenin plus ZL because of this particular notation also. This straightforward. VOC is by Thevenin plus ZL is equal to this ZL is equal to the load current. Right? Open circuit voltage. That you have to find because this is including the load condition we are talking about. Open circuit voltage is we are removing the load. So with the load voltage that is being considered, which is also referred to as the Millman's voltage direct computation, IL into ZL. So 20 by 11 into 3 is 60 by 11. That is the difference between the open circuit voltage and the Millman's voltage. So Millman's voltage is equal to VOC minus IL into Thevenin. It's not only of academic interest. Instead of finding the open circuit voltage and Thevenin for a particular circuit, it is advantageous to compute particularly for the like the case of the three-phase unbalanced circuits to find the Millman's voltage, which is same as the neutral potential. You don't have to solve this particular one directly using Thevenin's voltage, Thevenin's impedance, and other things. All these things. Voltage equal to V1 Y1 plus V2 into Y2 plus on plus 0 into YL divided by Y1 plus Y2 plus YL. So that means this is including this out. This is 0 is considered because assuming that the load voltage is not being having the current generator there, the current generator is 0 and multiplied by YL. So that is included in the denominator. Thevenin's equivalent impedance plus that is Thevenin's admittance. Okay, Y Thevenin plus YL. So that is same as 60 by 11. So and IL is equal to Vm by ZL. Instead of computing IL like this, compute directly Vm and then Vm by ZL gives you 20 by 11 is the load current. So there are two ways in which it is being done. So that is the essence of the Millman's theorem, where one essential point in this precaution to be taken is that for solving this particular problem, the voltage sources are considered to be in parallel. There is no element between them. Okay, and the load impedance also can be taken as the zero current generator one connected across it. So direct computation Millman voltage, which is same as the load voltage, which is same as VAB, is directly can be computed using this particular formula: V1 Y1 plus V2 Y2 plus on plus Vn by n plus 0 into YL divided by Y1 plus Y2 plus on plus YL. That gives direct computation of the Millman's voltage. So Millman's voltage divided by load impedance is equal to the corresponding load current. This is the usual, the standard. One more way of doing it. Not that this is not standard. This is also direct computation of the Millman voltage. This is the Thevenin's equivalent one. So always people will get confused. When we are talking about Millman's theorem, you talk about open circuit voltage first. So that is where people get confused. So this is a definite relationship between the Millman's voltage and the Thevenin's voltage. So I hope I made things clear to you. So this is next theorem mentioned. To my surprise, only superposition theorem and Thevenin's theorem, Norton's theorem, and maximum power transfer theorem are being written in the gate syllabus. But nevertheless, not the other theorems are related. But definitely they have given, they might have given the problems also, and you cannot ignore these theorems also. So therefore, I am concentrating. Don't knowing these things and spending so much of time on this. But I found these are very, very important theorems, and maybe in IIT pattern or GATE syllabus, etc., every point will not be given explicitly, but somehow only 4 theorems have been explicitly given there. Don't think that they are unimportant and like in other syllabi, it is out of the syllabus and other things. No question about it. You cannot have such type of situations in all India level GATE entrance examinations. Unless so, that is why probably one of the reasons where I did not given much giving the importance of the statement and theorems, because based on these statements only you can do any other calculations and even I don't know whether in three-phase unbalanced circuits Millman's voltage the nodal potential is to be computed or not. Okay, so if that problem is given, that has to be solved using Millman's voltage only, using Millman's theorem only. Okay, anyway. Okay, so what is the substitution theorem? It's a very important theorem as far as electrical circuits are concerned, and which is a prerequisite one for compensation theorem, which I will explain tomorrow's class. Okay, so after substitution theorem, I will explain intelligence theorem, which is a very simple one, and the substitution theorem is a prerequisite one for understanding the compensation theorem, which is very important. So, and in tomorrow I will explain that together with the loop current and nodal analysis briefly. Okay, so a branch in a particular network can be substituted by different sets of elements. Okay, as long as the corresponding that particular branch can be replaced with infinite number of the elements, infinite solutions can be obtained, as long as the network is unaltered and the network is unaltered and the current flowing through the branch where you are considering and the terminal voltage across that is same. In the original network, as long as it is same, then there will not be any difference, and between a pair of terminals AB, you can always replace it by another set of the pair of elements, or be a voltage source, be another branch, but or a current source representation or any such nature, as long as the voltage across that pair of terminals which you are considering, that is called the load branch. Okay, and the current flowing through that is going to be retained. The equivalent one can be done. So how this can be done is that will be explained now. And what is the importance of this is it can be substituted for a particular branch and inject this injection. Injecting means the giving the excitation source in the one direction to compensate for the, for example, you have the changes in the element values, which is in compensation theorem you will get subsequently. So, but application part I have to tell you at this point itself. So, if there is a resistance is increased, current will decrease. But I want to say that this is to be replaced. So, then you find the corresponding compensating voltage and introduce that compensation network pair that is replaced by Thevenin's one. So, Thevenin is removing the load and then doing the equivalent one. So, the substitution theorem implies it is a principle of the open circuit voltage and Thevenin's equivalent impedance as from the two terminals you will obtain. So, since that is unaltered, the network is not going to be altered. Whatever the changes that are made on the load side, when it is removed and equivalently replaced with other things, as long as the circuit load voltage and the corresponding load current under consideration, as I observed, it's not that some teachers might have done that, but I observed substitution theorem is not being taught in the regular content in electrical circuits, either in first semester or second semester. Or an impedance along with a voltage source without disturbing the voltage and currents in the entire circuit, provided the new branch has the source, same set of terminal voltage and current as the original branch. Okay, so this is a typical statement which is a that's what I said, with a voltage source or a current source or an impedance along with a voltage source without disturbing the voltage and currents in the entire circuit. That is a condition, another condition. Provided the new branch has the same set of terminal voltage and the current has the original branch. If you assume, but most of the times, power system problem taken care very carefully. So no dependent sources can be present. This is always people ask me the question about the dependent sources. So, and it is applicable to circuits having linear, passive, and bilateral and active elements. Okay. So I will now like to do a simple formula like situation. Where it is? Not written. Okay. Let me check. Yeah. Okay. I'm sorry, my mistake. I thought I have written, but anyway, that can be expressed. I will tell you now. So VAB is equal to V dash into V dash plus IL into some ZL dash. That is, if you want, you can write down that. That means the IL must be same, VAB must be same as of the original branch, and the remaining voltage source or the corresponding impedance can be made. Infinite number of solutions. Arbitrarily you can write. As long as these two conditions are satisfied. What is another voltage source? That is all you can take. So I repeat the statement of the problem. According to substitution theorem, any branch in a network can be substituted by a different set of branch elements with a voltage source or current source or an impedance along with a voltage source without disturbing the voltages and currents in the entire circuit, provided the new branch has the same set of terminal voltage and current as the original branch itself. So the branch in the circuit can be replaced by another set of the elements as long as the terminal voltage and the load current is same as that is there in the original circuit itself. So a part of the branch of the circuit can be replaced because of the reason that at the load terminal it can be replaced with the Thevenin's voltage source and Thevenin's equivalent impedance. As long as that is not going to be altered, whatever the changes you have made and the load voltage and load current are same, then you can also replace it by another set of elements. That is the meaning of this. So why that condition implies that the original network should not be changed, implies that to the left to the left of the load terminals, the network can be replaced by open circuit voltage and Thevenin's equivalent impedance. And that network is not being changed, so therefore there is no change on the network. But the configuration is only changed in the other end. But the condition that has to be satisfied is the voltage and the corresponding current through that particular branch in the original network which is being given must be maintained. So that is the essence of this one. So VAB is equal to V dash plus IL into ZL dash. So I will give an example here. Okay. So consider the circuit shown in figure. Consider the circuit shown in figure. So this is 10 volts and this is 1 ohm. This is 4 ohms and with voltage or current sources. Okay. So now this is a 10 volt source and 8 and 8 are in parallel. That is equivalent is 4 ohms and this is 1 ohm. Okay. So therefore the total load current is 10 divided by 4 plus 1 is 5. So total current delivered by the source is 2 amperes here and current gets divided as 1 ampere and 1 ampere through IL. So IL into IL is 1 ampere, so this is 4 ohms. So the voltage across AB will be equal to 4 into 1. So these things now are too elementary at this stage because it's a very simple circuit of element currents, right? So this is 4 ohms, this is 4 ohms and this is 8 ohms. So 4 and 4 are in series and it is 8 ohms. So therefore 8 and 8 are in parallel gives you 4 ohms, half of that. And because equal resistance are there and this is 4 plus 1 is 5 ohms is the equivalent resistance. These steps I have not shown because it is too elementary, okay, at this level. Come to the so many lectures now and you are already studied all those things. So there is no complexity in that. It is a simple circuit, DC circuit. So 10 divided by 5 is 2 amperes is the total current. That is what I have put here. The current total is 2 amperes. And using the current division rule, because the current branches are equal, resistance are equal, so 1 ampere of current flows through 8 ohms branch and this IL, that is through AB, because 4 and 4 are in series. So therefore IL is equal to 1 ampere and VAB is equal to 4 volts. So this one can be replaced with the this is the original one. So this is what is meant by substitution theorem states. This is the original network configuration with the equivalent circuit at the load side AB, which is to be mentioned within terminals A, B, is 1 ampere load current, VAB is the voltage, and 4 ohms is the load resistance. Now you can see this can be replaced with this. How? VAB is to be 4 volts, right? VAB is to be 4 volts, and I am replacing that by a 10 volt source, 2 ohms resistance only. Remember that. So if you ignore this, you can say that I have added 2 ohms resistance to this, right? So that means if you consider that 4 ohms to be retained as it is, I guess to be obtained. So V dash plus IL into ZL dash. IL and VAB must be same. VAB is equal to V dash, some voltage source, and IL must be same plus ZL dash. ZL dash is 2 ohms, not 6 ohms here. If you want to consider together with, so therefore the voltage drop is, there is a rise in voltage from this point, so minus to plus 10 volts, minus 6 into 1 is 4. So, realized, somebody asked earlier how these things can be realized. If such a realization is being there, then this is valid. That's what the substitution theorem says. Okay, how do you realize it is up to you. Okay, if you don't realize it, okay, you can use any of the other set of elements if it is not feasible, but it is feasible to have an independent an ideal source also, an ideal source having 1 ampere of current, which makes 4 volts of this one being produced, so that VAB is same and this one is same. Or you can have a voltage source having a series resistance as a practical voltage source and then do it. So everything is possible. So this is a very typical, most important theorem as I understand the importance of that. Because nobody has thought about it earlier, maybe that I observed many times substitution theorem is not being considered as a vital this one, and this can be done as a compensation theorem. That means next I may explain that subsequently. Anyway, I hope this is clear to you. Okay, because you might have studied in circuit theory, but most of the times I observed that substitution theorem is not being given sufficient weightage. As volts, 1 ohm, 4 ohms, 4 ohms, 8 ohms, find the current through IL. Substitute the branch current, substitute the branch AB with voltage or current sources. So this is 4 ohms load resistance, this is 4 ohms load resistance, this is 8 ohms resistance, this is 1 ohm, and this is 10 volt source. So I have done with series parallel configuration itself a reduction. So 4 and 4 are in series. So 8 and 8 on parallel gives you 4 ohms. 4 and 1 is in series, gives you 5 ohms. So 10 by 5 is 2 amperes, is the current delivered by the battery. Is the current delivered by the battery. So I have mentioned 2 here. So applying the current division rule, the current flowing through the AB will be, this is 8 ohms, this is 4 plus 4. So I into opposite resistance 8 by some of the all the 3 resistances here 1 ampere, and VAB is equal to IL into 4 is 4 volts. So this is being a simple problem, it is only part of the problem, therefore I have not given much weightage to showing the steps here, right? So this is 4 volts and IL is some 10 volts, arbitrary. It's not that only 10. How 10 is being obtained? I said infinite number of solutions will be there. You can choose any other thing as long as these 2 conditions are there. No dependent voltage sources. Anything annanga than ఏదంటే తీసుకునే మళ్ళీ కాదు. There are certain conditions. So if those conditions are satisfied, then this is source. The current is 1 ampere and VAB is the corresponding voltage. So they are, this can be written by a current source also. So this is the principle of the substitution theorem. And one more I would like to discuss. So next one is diligence theorem. So this is of academic interest in the sense this is based on the principle of law of conservation of energy. The total energy or total power supplied by the total power supplied by the sources must be same as the algebraic sum of the power that is being delivered to the elements. So it's a very simple statement. It is generally solution to this particular one. So sigma V into Ik must be 0. So that is one. So and the voltage drops around the network. So that is for the entire network. That means there is one more person states that as long as the loop voltage, the voltage across that and current through that one, the applying KCL and applying KVL, whatever they think, everything that satisfies, this also should satisfy that sigma of Vk into Ik, the voltage across the source or the element, I equal to 1 to n, all the elements, okay, independent voltage sources or dependent voltage sources and total circuit elements, linear, of course, passive, bilateral elements, non-linear elements anyway, it's not there. So total power that is being delivered by the source must be same as the total power consumed in the all the elements put together, or taking the algebraic sum of these things, it must be 0. That is the meaning of consisting of linear, passive, bilateral elements here. Okay, if any current sources are there, it's not that strictly everything is embedded in the any circuit. So whatever they are being present in the entire circuit, the only simple sentence is the power delivered by source must be same as the power absorbed by all the R1, R2, R3, R4 is designated. There is a 10 volt source. Total current is 2 amperes that is being obtained. Just now, power delivered by the source must be same. So now you can see power delivered by the source is V into I. So 10 into 2 is 20 watts. Okay. So power absorbed, power in each of the resistances, that is delivered negative by R1 is I1 square, I square into R1. I is 2 amperes, 2 square into 1, 2 watts. 4 is 4 watts. PR3 is 1 square into 4 is 4 watts. And PR4 is projecting the PPT. PPT already has been prepared, or the slides have been prepared. Minimum 15 album. Network theorems. Yeah, there are certain problems or queries in this one. Okay. Now I will be answering the question and answers, and later I will go to the next theorem. For that, one more slide projector. I mean, one more PPT is to be projected. There will be a half-minute break for that. Now, it is equal to open circuit voltage only. Yes, of course, it is open circuit voltage. So, synonymously, you can always use the terms. Why not? That means alternative words can be used for finding. So, such questions can be asked. Why the student thinks that it cannot be asked? But anyway, still he is not satisfied with that. I can give the email access to you so that one-to-one correspondence can be made. Okay, right? And it's a typical the Thevenin's equivalent impedance. There is a problem. On this, yeah. If you have done anything wrong or you are not satisfied with the answer, then only you can ask such questions. He is asking me. Suppose I want the open circuit voltage across the load, across the output termination. That should be done at the one-to-one level. So sorry, that is I cannot answer to this. But if I don't tell this, people might think that I am not can be obtained. You need to apply the principle of maybe superposition theorem or otherwise, and then try to do it. And because there is a voltage source here, there is a current source here, and other things. But unless you do, it is not possible to tell on hand. How do you find out this one and other things? You need some time to do it. So online lecture classes, you cannot ask me to solve online. Okay. Okay, I can give you only the tips and other things, but you explain how you are going to solve VOC and other things, which is not the question at all. If that question is asked, definitely I would have answered. But in the gate exam and the question is given is only the what to use this particular. But at the time of learning, no shortcuts, please. Okay, at the time of learning, no shortcuts, right? So that is where this question is effective, but the only thing is I cannot answer to this because it is not for public, because all the students, because the doubt is raised by only the thing that is on superposition theorem. who is also helping me in making this one, because I thought I will take second opinion. I asked him to solve it independently. So he said, we have concluded this formula, even if you obtain, integrate that and then start from fundamental, you will get this formula only. I would directly have one thing. Phasors of the same frequency only can be added. I have given this particular statement. How do you want to miss it? Missing doesn't matter, don't worry. So it's not that, you have tried to do it correctly, but the only thing is the statement which is and the other. So, although question is repeated, I don't mind, okay? Okay, so, and one person has repeated the same question, not only asking some other question, one person has repeated the question stating that how to find the open circuit voltage when R7 is 8 ohms is being given, and he said he got the value of root 2. Okay, whether it's correct or not is to be defined individually. Okay, the question is not being asked, so he has asked himself the question, you have gone wrong or whether it's right or wrong, then maybe I can answer. Okay, so therefore it is related question, but and asked by the same candidate, I think, but doesn't matter. So always we are ready to give the solutions to the problems. Otherwise, we will try to verify through our colleagues and other things, or consult other colleagues who are acquainted with these things, well equipped or acquainted, who can address these questions. It's not that only one has to solve and I have to clear your doubts. So, no, So now I would like to discuss compensation theorem. In some textbook, I found that maybe I thought this may not be possible to cover in the same day, but I could get some time because the questions that have been raised are too small. Because yesterday the coverages were less, and we have one. That is tomorrow's lecture. But anyway, I could get the time now itself so that I can cover at least one theorem today. Problems get exclusively get not much problems are being given in these things except for objective questions. I am not interested in objective questions because you can have a lottery or otherwise. I have to give you the solutions. So writing the solution, doing the problem, and then solving, projecting onto this takes probably a lot of time. So I am able to give you the which are readily available, and then because one more thing is explicitly it is not being done. So okay, anyway. So that is just to make again to start for the after the subject. So now is compensation theorem. So in any electrical network consisting of a formula for this also being given. So what is the meaning of this particular statement? Briefly, I want to mention, which are categorically stated in the substitution theorem statement. Whenever there is a change in network configuration, do we have to do all over again? That means someone using resistance network or a loop current method, I mean series parallel branches network reduction or loop current method or node voltage method or any other method which is suitable for finding the ease of solution. Whether it is easy or approach, series parallel reduction or otherwise, find current through each element, other things. Now it is easy to say, but you have to solve the network all over again. But the advantage of this substitution theorem, by injecting this particular one, the compensating voltage into the network, the original configuration must be same. That is one thing. Second advantage of this one is that you can find the changes in the currents directly. I don't know how to do current is entering in the way or the other things, but directly this compensating voltage, once it is being obtained by injecting the compensating voltage directly, and that is the advantage of this particular theorem. That means you don't compensating voltage into the network. Give the statement of the problem once again, and give a typical R is changed to R beta is equal to VC by R Thevenin plus R plus delta R. This can be AC circuit also. So delta I will be equal to VC by Z Thevenin plus Z plus delta Z. Now, these are some of the salient features of this particular semiconductor device elements, nonlinear circuits. So by injecting VC into the circuit, this is what I explained. By injecting VC into the circuit through the branch, the changes in the current in all branches due to change in the load resistance can be computed and replacing the original source by their internal resistances. This is direct computation of the changes. This is my own statement. I mean, people might have given differently, but this is typical statement based on the observation that we have obtained. We have been doing that in our lab, even at the first year level or whenever the lab is introduced in 2-1 or 2-2, wherever it is there in our curriculum. So, electrical circuits lab, we do this compensation theorem. Okay, so you hope you okay, but if there is a parallel branch connected, there the scenario may be different. So therefore, there will be changes in all the elements in the current in the network. There is no doubt about it. But so if the load, it will be aiding the source. Whereas earlier we have stated that it is to be put in opposition to the branch. That means if the resistance is, there are two issues here. One is if the resistance is increased, current will decrease in the load, no doubt. In order to compensate that, you have to inject the corresponding voltage source. You have to substitute the voltage, right? Because the resistance is increased, current will decrease. So you have to inject the voltage source. That is one aspect. Suppose now resistance is decreased, current will increase. Okay, in order to opposing the flow of current in the load, it has due to the changes in the resistance or impedance. What is the change in the resistance? Change can be due to resistance or impedance can be increased or decreased. If resistance is suppose this is voltage in the opposite direction, so that obtained as the changes in the currents in each of the elements. Changes in the currents in each of the elements can be obtained. Whereas the second case which I am telling is that if the resistance is decreased, current will increase. So in the load, right? So in order to compensate for that, it will be aiding the corresponding. It will be in the direction of the current that has to be done in this, but it will be aiding the voltage source. It find the changes in the currents also. How much is increase in current can be obtained. Okay, so this may be trivial on the face of it unless you are doubly sure about it. If you have studied this particular theorem and now trying to listen to me, probably you can understand better. Otherwise, it may be confusing to you because of the various options that are being available in explanation of the increasing resistance, decreasing resistance, increasing current, substituting the theorem by a set of branch elements and then reintroducing that one to find the changes in currents. So this is a multiple explanation is being given to this particular one. Okay, so I repeat this particular one. So in any electrical network consisting of a voltage with V Thevenin and resistance R Thevenin, delivering a load current I to a load resistance R, if the R is changed to R plus delta R, the change in current delta I can be determined by replacing the voltage source of magnitude VC equal to I into delta R. Thus, in series with the resistance R plus DR, delta R, with the polarity opposing the flow of current. Okay, so R plus delta R may be increasing the resistance, so therefore it should oppose. So current will be decreased. So you have to inject that in the opposite direction. Delta I is equal to VC by R Thevenin plus R plus delta R. Now second case, this is the salient features I want to explain once again, so that I want to work out a small problem which is of my own. So to explain what is I have explained. So you can do that by replacing the voltage source, the compensating voltage, you can find the change in the current directly. That's the typical nature of this particular compensation theorem based on the substitution theorem principle, which is linked with the open circuit voltage and Thevenin's equivalent impedance. For everything, Thevenin's theorem is based because prior to the network load condition AB, prior to the load terminals AB, it can be replaced by open circuit voltage and the Thevenin's equivalent resistance or impedance. Okay, for the given network. So to make T equivalent, you have to substitute the corresponding branch equivalent to the principle of the substitution theorem. Then when you substitute, then you can obtain the compensating voltage. That compensating voltage, that is the alternate voltage that is being introduced into the branch, can be useful for finding the changes in the current. The change in the current is to be put along with the change in this one, you have to put that in the opposite direction. Now, if the resistance is being decreased, current will increase. Then, in order to find the changes in the current introduced in the compensating voltage, you have to introduce that in the polarity of this one should be aiding the corresponding current, but the potential difference will be decreased. That you will observe subsequently. So therefore, by introducing like that in the other direction, when the resistance is decreased, current will increase, and to find the changes in the currents, this compensating voltage is to be injected in such a way that it should aid the supply voltage. And also, if you remove the voltage source, original voltage source in the network, right? If you remove the original voltage source in the network, you can get the changes in the current due to the resistance being decreased in all the elements in the network. In all the elements in the network. That is what the importance of this particular one. Okay. So it is not applicable to non-linear circuits. It is not applicable to circuits for having semiconductor device elements. And by injecting a VC into the circuit through the branch, changes in current in all branches due to change in load resistance can be computed and replacing the original sources by their internal resistance. Here you have to be careful about what is meant by change. Change in the resistance implies the change may be and explanation also will be this compensating voltage. Once it is being injected into the circuit, you are able to follow this. Terminology seems to be complex and no word can be cut in this. So it is a complete sentence that have to be understood carefully. Any Telugu explain cheyadaniki custom avutundi. So if the change in the resistance is there, change in the current will be there. In order to change in the resistance, it has to be compensated. So that compensating voltage is to be injected. The compensating voltage to obtain the changes in the currents also can be useful. So that is the most important thing. So how do we do that? Is resistance decrease aithe current increase avutundi. Kabatti the current should be such that the injected compensating voltage should be aiding the supply voltage. And to get this changes in the current in all the elements, introduce the injected voltage in the aiding to the supply voltage in the direction, aiding the supply voltage with the polarities, and replace the voltage source, the original voltage source by the internal resistance. Then only you can get the changes in the current due to the change in the resistance. That is, resistance is increase, current decrease, current flow should be same kabatti, and you have to put that. So now I would like to give an example on compensation theorem. So it is a simple problem, same problem which I have taken for ease of illustration always. Okay. And you can see I have tried to solve this same problem in a different direction and verified this particular one also. Okay. So verification. Find before doing verification. So for the circuit shown, find that is why I take some typical cases here. This is not a gate question paper. This is my own explanation I am giving you. If anything you find the difficulty, definitely I will clarify the loads. For the circuit shown, find the compensating voltage and find the change in current when the load resistance is changed from 4 ohms to 5 ohms through AB. Same circuit I have taken conveniently, right? AB. 4 ohms, this is 8 ohms, this is 1 ohm, so this is 10 volt source. So to find the compensating voltage, how do you find the compensating voltage? I into delta R. Now what is I? IL is 1 ampere. Same circuit. That is why for ease of explanation I have taken the same example for this method. Load current next loop current method ki node voltage kuda ade తీసుకున్నాను easy అవుతుందని. Okay, so that we will explain tomorrow and start 2-port networks also tomorrow itself, because there are only 2 more theorems. There is loop current nodal analysis, already you are familiar, already you have explained the basis also. Anyway, so now I repeat the statement of the problem. For the circuit shown, find for this previously just explained. Okay, so IL is equal to 1 ampere, so VC is equal to compensating voltage in currents can be obtained as delta I is equal to this formula, VC by R Thevenin plus R plus delta R. So for finding that you need to obtain R Thevenin. So to find R Thevenin, remove the voltage source, remove the load and find the voltage as viewed from the terminals, looking back into the terminals of the network AB. So everything is interlinked. I am talking about substituent theorem, I am talking about Thevenin's equivalent voltage source, I am talking about compensating theorem. Okay. So element current method you have used here, even loop current method used, nodal voltage analysis can be used for finding the current through this one. So they are simple circuits. So same problem if you take for different approaches, you can see which is beneficial. That is why I just have taken this particular example. Anyway, so for this particular formula to use direct computation of the change in the current through the load directly, VC by R Thevenin plus R plus delta R. Delta R is load, not 4 plus 5 is 9 ohms. Then it will be total resistance in the circuit will be 9 ohms across AV. But I have mentioned only 5 ohms. This R is known, delta R is known, VC just now we have obtained. Now we have to get the R Thevenin. So for that, remove the voltage source. So the network 1 and 8 are in parallel, 4 ohms is in series. So it is 1 into 8 by 1 plus 8 is 8 by 9 plus 4 is 40, right? And delta I is equal to VC by, I have used this particular formula, VC by R Thevenin plus R plus delta R. So VC is 1 divided by 44 by 9 plus 4 is 4 ohms is load resistance, this one, and delta R is 1 ohm. So is 0.899. Okay. Yeah, 0.899. So that is why for verification I have given multiple ways of doing it. As I said, I have mentioned one more aspect which I am not doing now. Take first circuit, find whatever may the way, find the current through each element. Take the second circuit with R is changed from 4 to 5 ohms. Change in the current can always be obtained. Instead of doing that, now I am not only verifying what is the change in the current, finding the new current, and also I will explain through injecting this particular one, injecting the compensating voltage. That also as a part of the explanation I have made. These are not necessary. Direct answer to this particular is only this particular one. Delta I is equal to 0.101 is the answer. That is over. But in order to understand this, I have given not clear, definitely you will ask me. And before, if I start explaining orally, I have to, if I write it, then I have to take a scan of it and then put it in the PPT and other thing. It's my own explanation. So I thought I will explain in this particular one. Verification is being done. So find the Thevenin's equivalent network at AB. Okay. So in order to obtain the substitution theorem for a branch to be replaced and then applying compensating voltage, you have to go back to this particular one, applying Thevenin's theorem. So VOC is equal to, so by removing the load, why and all? Because it is a part of the statement of the theorem. So this is another way of doing it. Here, direct computation or going through open circuit voltage, finding jet Thevenin, find the load current, and then find the changes in the currents, etc. So I am trying to do using Thevenin's theorem now. Okay. And there are other methods are also there. There is element current method, loop current method, nodal analysis can be made, all these things can be done, no problem. Because for the same circuit, for the same change in this one, the values must be same, whatever the methodology you use. Okay, for that I have just given. Ultimately, network analysis is only based on the typical condition. The network theorems have to be used at appropriate context. It's not that only one theorem is to be applied for a different context. You can apply based on the ease of solution to be obtained. You can use different kinds of the solution. The current flowing through this is now 10 by 1 plus 8 is 9 because there is only one loop here. There is only one loop. So the current is flowing through the circuit is this, and voltage across this one is VAV is equal to voltage across the 8 ohm resistance. That is why I put it is already familiar to you. That's why I put 10 by 9 into 8 is 80 by 9 volts is the open circuit voltage. Remember, it's not the load voltage. Load voltage is 4 volts, which you already obtained. So to find R Thevenin, so remove the load. Looking back to the terminals of the network, 1 and 8 are in parallel, 4 ohms is in series. So 1 into 8 by 1 plus 8 plus 4 is 44 by 9. So Thevenin's equivalent circuit is this. So VOC 80 by 9 and 44 by 9. And IL is equal to VOC by R Thevenin plus RL. So this is 80 by 9 divided by 44 by 9 plus 4 is 1 ampere. So instead of doing the series parallel connectivity will be done always for every problem. We need Thevenin's equivalent resistances or sources for computation. So IL is equal to 1 ampere. Same thing. Already you have got this direct computation directly because known values. I have not shown the steps here. So it is already series parallel branch reductions and finding the total current division rule, applying all these things are familiar to us. So, but saying maybe sometimes not very much familiar on without putting it on paper. So therefore I have written this. Okay. So VOC by R Thevenin plus RL is equal to 1 ampere. This satisfies the load current for the original network. Now you can see RL is changed from 4 to 5. No doubt VOC and R Thevenin are not changed. Okay, so the change in the current, the total current now, when this resistance is changed from 4 to 5 ohms means 1 ohm is added, 1 ohm is only added, remember that. 4 to 5 means, don't get confused, 4 to 5 means the value of the resistance across the AB is changed from 4 ohms to 5 ohms. Only 1 ohm resistance is implied to be added. So VO0 R Thevenin plus RL plus delta R. So 80 by 9 is not 8019. So it is 80 divided by 9 in the numerator, divided by 44 by 9 plus 4 plus 1 is equal to 0.899. So therefore delta I, change in the current, is equal to 0.101. This is one type of computation. Okay. So now I have to use the compensating voltage. So already compensating voltage has been mentioned. I have injected 1 volt source here. And in addition to the 1 ohm and 4 ohm, additional resistance which is included in the circuit also is to be shown here. So VC is the compensating voltage, right? So this 1 ohm and VC have been obtained based on the substitution theorem only. But how much is the substitution theorem says? Whether it is what type of source you are adding, current source or voltage source, conveniently you are choosing current source. Okay, so VC equal to 1 volt. And this is 1 ohm. So this also is to be included. Now direct computation of the change in the element currents will be obtained by replacing the voltage source. Original network voltage source is being replaced by internal resistance. Now compute the change in the current. So therefore, in this now current flowing through this particular branch is the change in the current in this. Okay, which is opposite direction. So current is reduced. So it is opposite direction. Again, lot of these things, sign conventions. The original direction of the current in the is from A to B. A to B not shown here. Okay, but now the current is from B to A. That is, current is injected in the opposite direction. In the sense, the voltage is injected because the current is reduced. How much is reduction in the current? Is the reduced value, the current obtained is change in the current is 0.101. So in order to obtain the change in the current, it is equivalent to you have injected the current in the opposite direction, this voltage in the opposite solution, the compensating voltage. So essentially compensating voltage uses substitution theorem based on the Thevenin's voltage network. Prior to the network configuration, it must be unaltered, and changes in the resistances can be computed for due to the changes in the current. Due to change in current, it can be substituted by some branch, and that branch can be obtained using the compensating voltage as a voltage source with the same load voltage and the load current that can be allowed due to the change in the resistance also. As long as that can be obtained, there is no problem. And you can verify that how to obtain the compensating voltage. Go back to the original network and apply this voltage in such a way that oppose this one, and then get the compensating the various cases, right? So the first one is finding the compensating voltage, and therefore delta I is obtained as 0.101. So that for verification I have found using the Thevenin's theorem. First I found the total load current original network, but the change in the resistance of 4 to 5 ohms, one additional 1 ohm resistance, I have found what is the current that is obtained is 0.899. So 1 minus 0.899 is 0.101. This is one way of looking at it. Or otherwise I can do this using compensating voltage directly also for finding the change in the current. So that change in the current of VC is to be applied, injected into the network by replacing the voltage source in this and retaining the network elements, including 4 ohms and new resistance also. Then find the current. This current will be obtained as a change in the current due to the in this particular branch, due to the change in the additional resistance in the circuit. So that is where otherwise you have to do all over. So that means direct computation of this one, finding the compensating voltage and injecting this one, will get directly the change in the current. Otherwise you have to do the network all over again for solving the problem. So that's all about it. Before we wind up, I will just briefly review over 2 minutes and then we will wind up. Just 2 minutes, I am going to wind up. So loop current method and node voltage analysis briefly, and then start with the two-port networks also. So that is a lecture scheduled for tomorrow. Discussed the reciprocity theorem and I thank the university authorities, Honorable Vice Chancellor, DAP, and Professor Hemchandra, APSA Chairman, for giving me an opportunity to take the online GATE coaching classes. And so Tomorrow we'll have next one at 2:55. Please be available. So tomorrow, any questions are being there for today's lecture, definitely we will try to take up. And tomorrow I will start with the loop current and nodal analysis, and also two-port networks might be started because loop current and nodal analysis are more familiar to you. If one or two problems which are given in gate examination or I found in nodal analysis, otherwise almost loop current method is very familiar to you. You have been using it. More formal statement I will give. Any salient features are there, I will explain tomorrow. And nodal voltage analysis, typical questions are one or two questions are there in gate. I will try to give them. I think one I have selected. Yeah, I think this is gate 2014. Tomorrow I will explain this. And so these two will be explained in tomorrow's lecture, loop current method and nodal analysis. With that, all the theorems, so therefore these are fundamental, so not much, already are more familiar. So therefore I have not taken much examples in this, and go to the two-port networks because I am not in a hurry to cover the syllabus, but I think I am giving it a slow pace only to make you understand the things. So okay, I hope because even now I may not be able to cover the entire syllabus, because tomorrow I will be completing the network theorems and start two-port networks, and I will be discussing on two-port networks only a few. There is impedance parameters, admittance parameters, transmission and hybrid parameters. Generally, we are not using much inverse transmission and inverse hybrid parameters. Out of the 6 combinations, we have got 4 to do, and after that two-port network, then we will go for transient analysis. Then still a lot of things to be done. Anyway, it doesn't matter, don't worry about that. Still we have got 5 days to go and 4 days for lecturing, and 1 day if 1 hour lecture and any queries are there, and we'll see how it goes for the wind up session on 22nd. Another